Next up, we have John Dickinson giving us an overview of Swift. Thanks.
Thanks. My name is John Dickinson. I'm the project technical lead for OpenStack Swift, and I have 20 minutes to tell you everything you ever wanted to know about Swift. So I'll do my best on that. Basically, I want to give an overview of what it is, the problems that it solves, and then a very high-level overview of architecture. I'll talk a little bit tomorrow at the OpenStack mini-conf about contributing to Swift, and then on Thursday, hopefully some playing with Swift and looking at some failure scenarios and doing that against a VM and seeing what happens. So the first thing is, what is Swift? Swift started back in 2009 at Rackspace as a replacement for the storage engine behind Rackspace's Cloud Files product. It was a rapidly growing product that was suffering because of scale and just not being able to be wow, what happened? Sorry about that. It was hard to manage as it was growing very rapidly, and it was having some major pain points as it was growing rapidly. So the Rackspace leadership said, we need something better. And so that's when Swift started. This is when I joined Rackspace back in 2009 and started working on Swift. It was launched into production at Rackspace in 2010, and then 2 months later was released open source under the Apache 2 license as part of the OpenStack project, along with another project that was contributed by NASA. So since then, since 2010, we've had extremely rapid community growth and lots of new contributions, lots of new deployments, and here are some of them. This was just some things I pulled together. These are people that have either publicly announced or talked about deploying Swift clusters or have actually contributed something to the Swift code base. Notice there's a lot of service providers here. That's generally because service providers are in the business of talking about the kind of underlying technology that they're using, especially when you're talking about open systems like OpenStack. But there are a lot more clusters than this, some of which I find out when anybody else does, and some of which I've heard about behind the scenes. People who are doing internal-only storage systems for their internal use cases. We originally started, when it released, with 10 contributors into Swift when it was originally open sourced. Those were basically the 10 developers who had been part of the project while it was still at Rackspace. Since then, we've grown quite a bit. We've had 94 contributors total into Swift, so if 6 of you write a patch, that's great. I can finally say we've got 100 contributors. The last release, which by the way was just last week, we released Swift 176. We had 25 individual contributors. Based on some questions that came up this morning as part of the CloudStack talk, somebody was asking about what's the diversity of the companies that are contributing here. I just looked through the logs very quickly. Looking at the Git logs, we have 48 unique domain names in the commit logs. And 28 of those are, not 28, one of those is Gmail, and we have at least 28 entries from Gmail alone. So Gmail is the biggest contributor in Swift right now. Anyway, my vision for Swift, long term is that everyone, everywhere will use Swift every day, whether they know it or not. And based on just some of these logos, you can see we're already doing some of that. So you pull up an image from Wikipedia, you're pulling it from their internal Swift cluster. Vimeo's working on Swift clusters to store video. Not to mention all of the thousands of customers that people like Rackspace and HP and Dell and other service providers have. So this is what we're going towards. I think we're doing a pretty good job so far. We've got a lot of room to go. So overall, Swift is object storage. It's not block storage. It's not a distributed file system. You can't mount it. It's not POSIX compliant. In fact, it relaxes some of the POSIX constraints that would be on a file system in order to achieve massive scale. So Swift was built for scale, and it's optimized for durability, it's a storage system, availability, and concurrency. So let's cover each of those in turn. First is it's built for scale. The design, which we'll go over in just a minute, is that there is no single point of failure in the entire system. There's not a central metadata layer that has to be queried. Any single part of Swift can fall over, and you're just fine. It's got a very modular design, and each of these pieces of Swift can be scaled horizontally as you need. If you need to add more space, great, add more space. If you need to add more front-end capacity for networking or connections, you can do that as well. Swift is durable, which really shouldn't need to be said because it's a storage system, and that's kind of the table stakes right there. But we achieve this by using full replicas of the objects. So by default, although it is configurable on a per cluster basis, Swift stores 3 replicas of your data in it. And it's more than just, hey, let's copy 3 replicas. It's actually a little smart about this and is able to place each of these replicas onto distinct machines, and if you have it, even into distinct availability zones. Why does it keep doing that? I apologize. We have active auditing and consistency checks within the system so that in the background things are going to ensure that your data is not only there but is correct. You don't have to worry about bit rot, you don't have to worry about drives failing, things like that are common in storage systems. And if there is an error, the entire cluster will participate in the recovery of that error, and so that you have a lower mean time to recovery than otherwise, because the entire cluster is participating. Swift is available, and if you know the CAP theorem, we sacrifice consistency for available. It's an eventually consistent system. So normally you want everything to be consistent, and if there are no errors, Swift will give you 100% consistency. But in the face of errors, say for example a hard drive has failed, or a server is down, or even a rack of servers is down, in that case you may fall into an eventual consistency window and not, for example, be able to see all of your objects in an object listing immediately. But that being said, there are protections against crazy things happening. So for example, if you have 3 replicas in your cluster, Swift will ensure that 2 of them are successfully flushed to disk before the customer, or the client, will get a success back. So you know that your data is written. If Swift gives you a successful response, you know that it's been written successfully to disk. It uses quorums for this so that a majority of your storage nodes had to successfully do the operation before you get that back. And we offer a per request flag on reads that if you need to, you can get the most recent data regardless of your current consistency window. You can say, give me this object, but query all of the servers and make sure you give me the absolute newest one that you have in the cluster. And that's possible. The other thing I mentioned is that Swift is optimized for concurrency. And by this, I mean that Swift was not written so that you can throw a bunch of, you can optimize a single stream and serve that up as quickly as possible. Rather, it's built so that you can have 10,000 streams at once or more, however many you need. And this comes out of what this lends itself to, looking at the use cases. So if we're looking at optimizing across many clusters, what are kind of some examples of how that will work? Generally, Swift is going to be good for any sort of data that is unstructured and can grow without bound. So, user data. Things where you're storing a little piece of information about users, or you have user-generated data. Say your users are uploading images or any sort of other content. Maybe you have a small settings file or something about every single user. Something that's just going to stick there that you don't have to worry about, but needs to be very available, and in aggregate can grow extremely large, both in the cardinality of your number of objects, but also in the aggregate total usage of your storage space needed. Another great use case for Swift are things like web content. You're serving images, which obviously, if it's the internet, it means you're serving cat pictures, right? And so Swift is going to be great for this sort of thing. I used the example of Wikipedia earlier with their cluster. Swift is really good at storing and serving static web content like static HTML files, JavaScript, CSS, images, videos, things like that. And because Swift is simply using HTTP and a REST interface, it means that it works extremely well with things like caching layers and CDNs and stuff like that. So when you're looking at web content, you get an access pattern that looks kind of like this. You've got some really, really hot content and then a whole bunch of content that is not quite as accessed quite as often. And so, say in Wikipedia, if you look at the front page content versus, say, the images served off of the article on B+ trees, as much as we would like to think that here, it's probably not the most popular article on Wikipedia. So because all of this data has to be available, you've got this aggregate concurrent usage. I'm sorry about that. The aggregate concurrent usage ends up being long tail, and Swift is good at that. Other examples of this would be things like looking at bank records. How come you can't go to your bank's website and pull up a statement from 3 years ago? It's not because they don't have that, it's because it's been archived off on tape somewhere and it's in a warehouse across town. Or if you're looking at scientific data, something that you've got a set of data that is very large and is literally impossible to recreate because it involves, I don't know, crashing something into an asteroid or something like that. But at the same time, you have to have this data available for a long period of time. You need a storage system that can reliably store this kind of long tail access pattern. Another use case that Swift is very good at is mobile content. And the difference with mobile content, as opposed to just generally web content, is the fact that there are billions of mobile devices all over the world. And so you generally have to deal with an extremely high amount of concurrency. So for example, maybe you think that mobile gaming is going to be the next hot thing. And you need to store avatars or how many little trinkets your users have or something like that. You need to store this data on a per user basis. This is kind of this highly concurrent per user information that Swift is really great at. So we've seen kind of the overall use cases. So how does it do this? Looking at the overview, very high level overview of the architecture. There are 4 basic parts of Swift. Looking here, here's an example of a URL. I mentioned that Swift has a REST API, so every object in Swift is uniquely addressable by a URI. And here's an example of one. The prefix here you've got up to the /v1 is simply just the domain name and saying, hey, we've got v1 of the API. And then you've got 3 parts here. You've got the account, the container, and the object. Swift is very conceptually similar to something like Amazon's S3. And so you've got some of these same concepts here. You've got the account at the top layer, which is a segment of the overall namespace that's allocated for one particular user. You've got containers within that, which is similar to Amazon's buckets. And that is a per user namespace slice. And then everything else is the object. The first part here is the proxy. The first of the major 4 parts here is the proxy server. The proxy server is what implements the API. So basically, that first part of that URL. The proxy server is what talks to the client and what coordinates responses and requests and responses to and from the back-end storage servers. The next piece are, whoops, there we go. The next piece would be the account server. The account server is what is responsible for the accounts layer, and it contains a listing of all of the containers and a little bit of metadata associated with that, say the aggregate total bytes used, the aggregate total objects, things like that. The containers are very similar and store some aggregated metadata and also listing of the objects inside of them. And then the object server is what stores the actual data on disk. But in reality, you're going to have many of these each in a Swift cluster, and then you can scale those out as you need to. Going very quickly on the next piece, we've got the ring within Swift. Swift uses consistent hashing and with some enhancements on that. In the interest of time, I'm going to skip over a little of this. But the basic concept here is consistent hashing. A request comes in, you figure out where it lives based on the hash of something. You make it a little bit better by adding more virtual nodes. I can answer questions on this in just a little bit. And then what Swift has done is takes divides the overall namespace, the key space that is used, into equally sized chunks. And this allows us to simply hash the name of an object, take the first few prefix bits off of that, and then do a direct lookup and figure out what partition of the overall key space we need to, and then we know exactly what storage nodes those are mapped to. This mapping of the key space to the storage nodes is the Swift ring. Swift does some very nice things about being able to make sure that you have your mapping is your replicas are going to be in distinct availability zones so that you can suffer, say, a failure of a particular rack or a DC room or a certain power supplier. The final thing about Swift that I wanted to mention is that we've got active integrity checking on the back end. We keep checksums of all of the data. We compare that checksum with what's stored every time the data is read off of disk to ensure that there has been no bit rot. We continually walk the drives to make sure that there is no file system corruption or bit rot on that kind of thing. We've got replication running in the back end. We do active checks on making sure that your drives are still mounted, they're still valid, they're not throwing errors. And all of this works together then to provide you a very highly available and reliable system. And if you want to see more of these things in action, come to my talk on Thursday. So if you have any questions, I'm going to be giving another mini-conference talk, Swift for new contributors, tomorrow in the OpenStack mini-conf. And then on Thursday, we've got Playing with Swift to talk about some of the failure modes. If you, I work for SwiftStack. We provide tools to help you run Swift clusters. We've got a lot of information about Swift on our website as well. If you want to look at some of the docs, swift.openstack.org, and the code is hosted on GitHub. Questions?
Yeah, so what's the minimum number of physical nodes to actually run a real, I know you guys probably are part of the OpenStack, DevStack or whatever they've got, but for an actual production, what's the minimal number?
I would recommend that you would have at least 2 so you could suffer the loss of one of them. But if you look at nodes as servers rather than hard drives, you could run with just one server with multiple hard drives in it. You're going to want your replicas to be on distinct physical drives. So if you have at least 2, then you're protected against at least one drive failure. But the more the better. Yes, and in that case, you're going to, it's going to kind of fake and say you've got 3 when really you've just got 2. But that's kind of a weird edge case. If you've got 3 hard drives, you're going to have 3 full replicas of your data.
To follow on a related question, you said there's 4 key parts. There was the proxy, and then the 3 other services.
Sure. Proxy, account, container, object.
So do we, in production, do we expect that each of those to be like a physical or virtual machine, or do we sort of bundle these as one thing?
You can deploy that either way. Yeah. Oftentimes, many deployments will run all of these on one box, and then you can have different. You can have many of those boxes kind of all in one, sharing responsibility. That's completely okay. Larger deployments generally end up optimizing some of those and have a separate proxy layer behind a load balancer combined with some sort of segmented storage nodes, say maybe account and container deployed one way and the object servers deployed another way. It really depends on how many SKUs you can get away with buying and what your actual needs are. For example, Rackspace's use case with a public storage provider is going to look very, very different than a bank or a Wikipedia or anything like that. So you can really tune it to what your needs are.
Quick question. Any plans to implement nested containers? Nested
containers are not supported. It's a very flat namespace. You have accounts at the top, containers underneath that, and anything under that is objects. But you notice everything was separated with a slash. You can have pseudo-nested directories and kind of simulate a directory structure, but it's not a first-level concept within the API.
Yeah, what languages does Swift have bindings for, and do you support Boto in some way?
So that is a great question. Swift is written completely in Python. It has language bindings that I know of for Python, Ruby, PHP, Java, C#, R, and maybe one more that I know of. And what was the last part? Boto. Swift, there is a community-supported Swift 3 middleware that you can run that provides a somewhat of mapping between the S3 API and Swift. It's really intended to be a something that you use for migration purposes. We really want you to use the first level, the Swift API over S3's API for various reasons. So, yeah.
Yeah, at the other end of things, what does a typical large-scale deployment of this look like? Do you have this, in one well-connected cluster and then another one somewhere else around the world? Do you have lots of objects? Do you have to blow out the object servers or something? What does that scale of that in?
No, that's a great question. So as of today, right now, each Swift cluster is going to be practically limited to probably a metro area. And it can scale extremely large. So I know that Rackspace is running many, many petabytes, many, many billions of objects within their cluster. And so that is deployed in such a way that they've kind of segmented out proxy layers versus storage layers so they can optimize how many requests and the external networking that they need based on the actual hard drive capacity that they need on the back end. And so that'll be deployed according to their needs based on their availability zones that they have set up in their data centers and things like that. But that being said, right now, there are people, including at SwiftStack, working on supporting global clusters so that you can have one logical Swift cluster that is distributed in basically a high latency environment, which essentially means transcontinent, around the world deployments. So it's being actively worked on.
I have a question in regards to hardware setup for Swift to achieve best performance, and in particular, I'm wondering about the core to disk ratio.
Yes.
What would you recommend? What baseline would you recommend?
I have no idea. It depends on your data needs. And that's not to be flippant though. The reality is you need to match that based on your particular deployment. So it may be that you just kind of have a general purpose thing you need to support most use cases pretty well. And then you may end up with something, this is, I don't know, one proxy server to, I don't know, 30 object servers. I don't know. It kind of depends and based on your hardware platform, based on your actual data use case. That is a question that comes up quite a bit. Actually, our company has to answer that for people quite a bit, and we have to do a lot of discovery on, okay, well, how are you going to use this? Nobody knows your data better than you, and so I've got to ask you actually, are you looking at a lot of hot content? Are you looking at a lot of cold content, something in the middle? Those things all play in, and the general answer is you can adjust your deployment based on what you need.
Okay, thank you.
Sorry for not a specific number. There isn't one.
We're actually just about out of time, but there's like 3 questions in my mental buffer here, and there's one here and one here and one down there. So if you can take that, ask the question, ask the team, and I'll
Okay.
So unless this has changed quite recently, I don't think object-level ACLs were supported. Is that on the roadmap?
ACL support is somewhat specific to the auth system that you're using, which is quite pluggable within the system. Generally, we try to keep things stored, things like that grouped on the container level, so that you have container level ACLs. Reason being, it's a lot easier to scale, several 100,000 containers rather than several billion objects. And just the overhead metadata gets large when you're dealing with that. So normally it's done, all the auth systems that I know about implement that on a per container basis. I don't know if they are planning on changing that. I'm not planning on writing that for any of them.
Yeah, go ahead.
Oh, yeah, sure.
Cool.
I'm sorry, what's that?
Do you recommend RAID for resiliency or potency or performance?
So the question is, do I recommend RAID for anything? And the answer is no. Do not use RAID with Swift in general. RAID 5, Swift will manage where the clusters work, where the replicas are placed on the different drives. It turns out that when you have large RAID volumes trying to back on these things, this is something we did when I was at Rackspace, it's pretty horrible because Swift does lots of small random reads and writes based on the active consistency and the whatever load you have on it, which is pretty horrible for RAID 5 and 6. And also when you get large RAID volumes, the recovery time on those is really, really bad and the performance just tanks. So put up some JBODs and that's it.
So similar to that, is there any data consistency and redundancy options other than just full copies?
No. You can set the replica count on a per cluster basis, but no, that is not, there's not another way to ensure you can't say, hey, on this set of data I'm going to do something else, or I'm going to choose to use erasure encoding over here, or something like that.
Parity inside Swift rather than parity underneath.
Right, correct.
Okay.
Sir, Florian?
You can repeat this one. When are you going to align your release schedule with the rest of it?
Do you want,
That is a great question. We are completely aligned with the rest of OpenStack. The OpenStack release schedule is every 6 months, and the OpenStack project says that within that 6 months, the projects are free to choose the release schedule that we do. Swift chooses to release historically about every 6 weeks, and every release that we do is production ready. You can upgrade your cluster live with no downtime for your clients. Happens all the time for some of these public deployments. And then we participate in the combined OpenStack release every time that happens.
we're going to have to stop there. Sorry.
I'll be happy to answer other questions and also at the other talks this week.
Thank you, John.
Thank you.